Alright, so the first vocabulary word that we're going to define is frequency. And frequency we're just going to define as how many times something happens in 1 second. So you can think of this as when there's higher frequency, that means something is happening faster. So with electromagnetic radiation, everything on our electromagnetic spectrum, when we say that part of that spectrum has a higher frequency, what we mean is that this electromagnetic radiation is just going back and forth at a faster rate. And we can describe frequency in cycles per second. And that's kind of the most basic way of describing frequency. But because cycles isn't really a unit the way that like meters or seconds or some of this other stuff that we'll do throughout the year is, we can just write that as 1/seconds instead. And because frequency is so important, we actually call a 1/seconds, that's equal to a hertz. Put that up in a different color so it's easier to see. And very closely tied to this idea of frequency is a wavelength. Wavelength is just how long a wave is. So if my wave looks like this, my wavelength just describes how stretched out that wave is. So one wavelength might go from here to here. So that's one wavelength. And that's measured in meters. Energy, you've probably talked about energy in other classes, but I might give you a different definition than you've heard before. We're going to define energy in this class as the ability to do damage. We don't need to worry too much about what that means. We'll spend an entire unit later on about energy, but I think it might help you make sense of the higher the frequency of this electromagnetic wave, right, the greater its ability to do damage. Those gamma rays, they can cause the most damage because they have the highest frequency and have the highest energy as well. All right, and I think diffraction I talked about a little bit in one of my previous videos, but I want to give you a little bit of an idea of what it means in addition. So I think we talked about things diffracting around barriers, and specifically waves are going to be the things that we think of as diffracting. And what do I mean when I say it diffracts around a barrier? Well, I can think of a barrier with a little hole in it, kind of like this. So maybe, there's two things like that. And then a wave is coming in on the other side, right? So it's looking like that. Some kind of thing where there's a wave coming in. And then when it goes through, it's not just going to go through the part where it goes, through there. It's going to diffract around the entire thing. And that's the diffraction that we're talking about. And you can help yourself remember it if you can come back to this picture, because that kind of looks like a D. So that's a D for diffraction. And you can think of that in contrast to momentum, because momentum is going to be a property of a particle. And because particles have momentum, they don't diffract. A true particle wouldn't diffract. It would just bounce off of other things. So we can think of our barrier, and let's imagine, to illustrate this, we have 3 particles. Right? The ones that hit the barrier, they're just going to bounce right back. This one's just going to go in and bounce right back. And this one's just going to go straight through. And if I had a whole line of particles that were all going towards the middle, only the ones that went straight through to the middle would go through, right? You wouldn't have any over here or over here. Sorry, it looked like one of my particles didn't match up very well. But the idea is the particles wouldn't diffract through the barrier. They would either go straight through or they would bounce right off of it. All right, and we're also going to go over this conservation of charge. And the conservation of charge is kind of like the conservation of energy. It just says that charge cannot be created or destroyed. So that means that as two objects that have a charge come together, their charges can get distributed between them. And then when they separate, their total charge has to stay the same. So we can work through these examples, right? If we have a -4 charge over here and a +6 over here, we have a total charge of positive 2 elementary charges. And afterwards, that's going to be evenly distributed between these two circles. So we have positive 2 elementary charges divided by 2. So we have positive 1 on each. And then in this case, we have positive 6 elementary charges and positive 4 elementary charges. So we have a total charge here of positive 10 elementary charges, which is also distributed between our two objects here. So we have positive 5 elementary charges here and positive 5 elementary charges here. We can go on to the last one, right? We have 3, but if they all come together and then they all separate, it's going to work the same way. We have positive 10 plus positive 10 minus 2. So we have a total charge here of positive 18 elementary charges. And that's going to be broken up into these 3. So we have 18 elementary charges divided by 3, and I have positive 6 in each of them.